for attending this webinar. It's a pleasure and an honor for me to speak to everyone. What I think is something that has been taking my thinking in the last few years is about complexity, and I entitled this Evolution of the Copper Industry over the Past Decades, Addressing Complexity and Looking into the Future Challenges. I am Gerardo Alvear Flores in Spanish, Gerardo in English, Gerardo in Japanese, and Geraldo in Brazilian, Portuguese, whatever you want to call me. Currently, I'm a adjunct professor at the University of Queensland in Australia, but also I work as an independent consultant. And also I am active member of the American Metallurgical Society, TMS, as an international liaison officer. If you want to reach me, you can reach me to my private email at any time. So let's see whether this will work. Next. Okay. So what is the motivation of this? The copper industry has made a lot of efforts in the last 4 years, in particular in the area that I work, that is smelting and refining, also in mining. For people who understand the flotation process, for example, on the concentration side, it has only 100 years of history. Therefore, has been made in improving energy efficiency, increases sulfur capture, adapt existing processes to decline copper grades, develop new copper processing technologies, optimize to recover valuable elements, try to address the environment by developing more friendly technologies, improve on the equipment side, given the high needs for productivity, and also developing synergies to maximize the recovery of valuable elements. However, we have new challenges. We have the challenge that give us the green economy, the decline grade of the ores, global warming, the need for recycling, the nationalism present in many countries, poverty, supply chain the last years with the COVID, CO2 emissions, lack of water, and of course, social unrest and issues, especially in the countries who produce the minerals, where in which countries people are also claiming to get some share of what is developing. So in this context, let's try to review what happened in the smelting industry in the last 50 years. Let's see how far we progress. Can we continue doing more of the same and achieve different results? How we solve the challenges of the green economy, considering all the technical, economic, social, and geopolitical restrictions that this imposes. How we have recorded this view, this technical view. In front of you, you have a book called Extracting Metallurgy of Copper, the first edition in the 80s by Professor Biswas and Professor Davenport. That has been a reference book for the industry for more than 50 years now. I studied with that book in the 90s, and I have the honor to be invited by Professor Davenport and Professor Schlesinger to work in the last edition, who was published last year. And also, I have recorded my view with my colleagues Carlos Rizzo-Patron and Joe Pease in this article, Processing of Complex Materials in the Copper Industry, that is public, open, you can search that on the internet. So the story that I want to tell you started in the 70s. And in the 70s, you remember we have a different world. We have the first oil crisis. We have the men reaching the moon. We have the personal stereo from Sony. We have the revolution in Iran. We have Watergate. We have Vietnam. We have Bill Gates. We have Stalin. We have Reagan. Floppy disk started, for many of you will remember, Texas Instrument calculators. And we have in Chile, in my country, end of the nationalization of copper and a new government. So in the 70s, when this book was written, two challenges were identified. So our view was merely, I will say, focused on the technical facts. So first was, things are becoming more expensive from the energy point of view. The technology was basically using oil as a fuel for smelting, and we used to emit all the gases, as this is shown, with SCO2 going to the atmosphere, given the restriction of the technology to produce acid at the time. So then it started what the copper industry called the golden age, with a lot of knowledge generation on the process fundamentals, developing new smelting technologies, focus on new methods for smelting, so basically increasing productivity, use of oxygen, as was done in the steel making. We start to capture the sulfur, so we start to develop the acid plant technology more. We start to capture the secondary emission, those that couldn't go to the acid plant. We start the electro-refining transformation with permanent steel cathodes. And then automation. So if we look now and we try to put in three different ways, 1970, 2014, and 2023, what challenges we identify? 70s, energy and sulfur. 2014, we start to think about financing and managing capital projects. Many projects were becoming more expensive. We start to address sustainability. We start to worry more about regulatory and reporting requirements, managing risk, improving performance. There was a consolidation in the industry with many mergers. And we start to talk about retaining the skills of the workforce. What we see today, we start to accounting practices for sustainability. We look for new sustainable products. We look for a way to identify those who produce more sustainable. We are pretty much worried about climate change. We are putting money on R&D for sustainable products. We think about decarbonization even more. We understand that we don't have all the water we need. We try to address circularity by minimizing waste, and there are a lot of efforts also in trying to work on tailings for recovery of minor metals, and also with energy efficiency in terms of its utilization. From the smelting industry, if we write a timeline like is shown here, at the bottom we have 1973, at the top today. In the 70s, we have an explosion of technology development in Canada, in Japan, in Australia, in Chile, in Russia, with a lot of technologies put into development and with the first installations coming into practice. We got to the 80s and 90s, and with the 90s, with the flex continuous converting in Kennecott, the Noranda converter in Canada. We went into more development with the bath smelting, with the Teniente technology, with ultra-dense phase injection. We work harder more in cooling elements. We start to process complex materials in the early 2010 with Mr. Alice roster. And then we have suddenly an explosion of technology in China with several technologies that have been, in a way, some of them improvement of the existing ones and other innovation. And the Chileans also start a very aggressive investment to capture sulfur to higher levels. When we look on the indicators on the right side, we have, of course, the consumption of copper is coming on the first one, increasing quite dramatically. And you said from 1970, we went from 8 to about 25 million in 2020. In terms of smelting capacity, the second graph, if you look at 1995, most of the smelter were what we call small plants with less than 1 million tons of corn, that is shown in orange color. And we went to mega smelters that shows on the yellow color on the right hand, over a 1.5 million ton of concentrate. In terms of a specific smelting rate, as shown in the bottom, we went from 20 to 30 tons to about 250 tons. So clearly this shows an economy of scale approach to increase productivity and deliver the copper that was needed. So what are the trends today? Basically, we live in a push and pull situation. The trends on the markets that are from the technology point of view, from the resources point of view, from the environmental pressure point of view, from optimization. On the resource side, of course, we have complexity. Complexity understood as decline of the ore grade, complexity understood as a need to mill and grind finer to recover the copper. Complexity understood in terms of products that are recycled, that goes from 2 or 3 elements to over 50 elements containing the particular device. Complexity in terms of recycling of those devices having several elements, as is shown here. From the response from the technology innovation has been clear, developing more intensive technology with the use of oxygen, more energy efficient technologies. On the environmental side, we have the pressure from the carbonization, the issue with the water in many countries in which water is a commodity that also need to be shared with the need to feed people. And on the optimization side, we have Industry 4.0, the need to increase automation, supply chain optimization that has been impacted in the last few years by COVID, as we see. And this poses a question whether the current model of shipping resources from the north, from the south to the north, is the right approach or not. And also, I would say the optimization from the multi-metal recovery point of view, where the main paradigm that is a mono element producer, let's say copper, understand the need to recover other containing elements. And how do we develop a pricing structure and a market that can, in a way, pay for that? Because it's time to remember that copper minerals do not come alone. They are a kind of minor metals. As you can see, copper ore will come at the bottom of the figure with iron, calcium, silicon, mercury, antimony, lead, silver, zinc, gold, molybdenum. And some of those are core metals that have considerable own production infrastructure. When we talk about copper, moly is a subproduct, zinc can be, lead can be, and some elements that are co-elements but ending residues or emissions like mercury or arsenic or antimony. So each carrier commodity metal is associated in nature, in geology, with a unique blend of valuable minor elements, as well as harmful elements of no economic value, which are lost through the processing chain. And this is at the core of the economic model that we need to understand how we will address that. In particular, if we remember arsenic I consider a bipolar market because we have the blend of arsenic increasing gradually, that content of arsenic in the concentrate is imposing a challenge to smelters who need to capture arsenic. That means they need to invest more dollars, but not produce more copper. So the processing becomes more expensive. Also, we have a technology that is considered base available technology that was developed in the end of the 1940s, like flash smelting, that basically they pour most of the arsenic to the slag, and that imposed a challenge to use that particular material as a secondary product if that arsenic is not stabilized. So what are the challenges for the miners? In terms of complexity, new mines and plants are more complex, deeper, and more expensive, with lower ore grades, with the exception of course, of some mines that are having high-grade ore, but not all of them. If the copper content goes lower, of course, we will have large amount of mineral waste that can pose threat to public perception of health and safety. Also, falling copper content in concentrate trade basically mean more impurities adding to higher downstream processing costs. The practice of blending with clean cons will become more challenging as the overall impurities level will rise, and traders will need to understand and look for new economic models to continue making money with their business. Also, the competition for water and access for water is becoming more difficult, and in a way, the social license when you have mines developed in agricultural zones become more difficult. These figures show you 32 major trade concentrates with the particular mineralogic composition calculated from the assay data. What is saying this figure is mines are moving into deeper areas with increasing primary mineralization, that is a higher proportion of copper is contained in chalcopyrite concentrate grades of traded con, meaning the copper con is going down. Copper content in the copper concentrate is going down. So concentrators need to improve, and in order to do that, they need to increase the mineral processing power, meaning they need to they need to do more fine grinding and flotation. This means more capital investment and more operating costs. But many of those operators will choose to pass the lower grade concentrate to smelter instead, as long as their concentrate is marketable and the penalties are less than the required capital and operating costs. So what is the impact on quality on this? Lower copper concentrate means an impact on the heat balance of the plant, more slag generation, more copper losses, difficulties in the slag that is being generated, more flux, more sulfur production, again, impact on the heat balance of the furnace. If you have more lead and zinc, you may need to recover that, but also you will have an impact on the anode quality. Another deleterious elements may increase your operating costs, increase your issues with environment, and impact on the use of the slag as an alternative market. So what is this smelting business? This all figure of this miner blowing with a pipe air into a mineral to produce copper. It's basically a box in which we add a lot of material, concentrate, fluxings, reverts, coal. We put oxygen in the form of air or oxygen, and through that process, we generate a gas, slag that is dischargeable, and a copper matte that is basically a concentrated copper material. But how we navigate into this process, how we understand how we process the material, how much air we need to add in order to achieve the quality we want to do. And basically, it's like having a GPS in your car or a map in which you want to go from A to B, let's say from South America to Asia. Your plane will have a particular route to follow, given by the navigation. In the smelting industry, we have also a navigator called the Yasawa diagram, in which rather than north and south, east and west, we have oxygen and sulfur partial pressure. And that particular navigation route allows us to say when to move from point A to B, to C, and then to E. By managing these two quantities, and therefore going step by step, we can manage the recovery and the product quality. Also, as in orienteering, we need maps, and those maps to manage the quality are called phase diagrams that you can see here that I will not explain, but basically base diagrams are navigation charts that allow us to get from A to B with minimum losses and maximum efficiency. So let's think about technology and flowsheet development. So basically, technology is a mixture of navigation tools, like I showed before, hardware, software, and know-how. And all of that coming together to produce a solution. That solution is what we call a simplified copper smelting process, in which copper concentrate coming from the mine and the concentrator, we go to a first smelting stage to produce copper matte, a slag that will go to flotation to recover some extra copper and produce a tailing, a gas that will go to be clean to capture those deleterious elements, and then the sulfur that will go to produce sulfuric acid. The copper matte, where the copper is, will go to a second stage called converting, in which will produce the blister copper that will have now 98%. So we went from 20 to 30 to 60, 70, and to 98. We will do the pyro refining, produce a copper anode with 99. We'll go to a tan house to produce copper cathode that will go to the market and to the fabricators. And we will get also the gold and the silver to produce precious metals. This is basically how know-how, hardware, and software are combined to produce the copper. Through that process, all that wheel of metal that we have will separate the materials into gas and dust, slag and copper anode, and different elements will go to different streams. Some elements will go to the wastewater treatment plant, others will go to dust processing, others will be recycled with the concentrate or disposed, others will go to refinery to the bleed to recover, like for example, nickel, others will go to the slime to produce precious metal, and the copper anode will go to produce the cathode. So this figure basically shows that most of the elements that come with copper get evenly distributed among different phases, and they have to be whether recovered, safely disposed, or recycled. Only the precious metals are preferentially captured by the copper phase and go to the slime processing and to recover of them. So here we have elements that are profit or cost. So the smelting business is basically saying, I have elements like precious metal that are profit driven and will go to the copper with the copper to the refinery. Other elements that might be profit driven, potentially depending on their concentration and the market condition, but gets distributed among the different phases. And other that basically are liability to the smelter and basically cost driven because they need to be treated and stabilized before they're disposed. Now, how we process secondary sources of materials? What we just described before, primary mining resources, but we have urban mining resources that are treated in especially developed plants for secondary smelting, or can also be added to the primary copper smelters and then be recovered. At the end, both will produce an anode that will go to a tan house. Depending on the grade of those materials, some of them may be able to be used here, but mostly will come through this. You see now that there is an explosion of business in USA in particular for this particular stream, in which, given the availability of urban mining resources, more people are starting to develop business on secondary material. So when we look at these two different ways of treating material, primary or secondary, there have been several efforts in the last 40 years to reduce the energy consumption, to increase the sulfur capture, to adapt technologies, to optimize the recovery, to be more environmentally friendly, and to increase productivity. And finally, try to develop synergies to recover valuable metals. So how is complexity then? Can we just do more of the same? Well, Albert Einstein defined insanity as doing the same thing over and over again and expecting different results. So the question is, how much can we increase feed rate and expect to achieve the same result? It's clearly as copper grade decline, we may increase feed rate, but we may not increase the copper units. So how we decode complexity? Through the value chain optimization, smelter knowledge, the knowledge of mineral processing, and the customer knowledge. So we need to optimize this equation and trying to combine all those elements to get to a more sustainable solution to produce the copper units we need. So we need flow sheets that with interaction that involve multi-metal recovery. And we need to understand that some of those elements are profitable and some of them, they basically become a liability. So the ability to recover those metals will depend on the minimum concentration level that we may have in the stream. So we may need to recycle intermediate stream until we achieve some minimum concentration. The opportunities in market to commercialize them, the local regulations that we may have, and the degree of integration with other base metals, lead, nickel, zinc. Smelter processing a standard concentrate will normally recycle stream until achieving a degree of concentration, in which case they will proceed to bleed some of this to unlock fresh capacities. So, economies of scale versus scope. Miners understand the nature of the resource and the opportunities. We have to understand the nature of the resources and the opportunities that resource gives to us. Copper doesn't come alone, as shown here. Some Western smelters understand that to survive, they need to develop capacities that not necessarily allow them to compete in the cost universe. Base metals operation integration is therefore required to ensure proper and efficient multi-metal recovery. So this is where I want to say that there is a push and pull between scope and scale. The right hand shows you a typical interaction that we will expect to have between nickel, copper, zinc, and lead operation by exchanging different products to try to optimize the production of these metals and increase the recovery. You will be able to read this when you receive the copy of the presentation. And this is basically a comparison between a scale of a scope. But what I'm trying to say here is that if we continue to think of as mono producers, it will be difficult for us to move from scale to scope. So we need to understand what are the potential synergies with the strategic partners in the base metal field for a given operation. How we can exchange product with a lead operation, with a zinc operation, with a nickel operation. How a smelter asset can be used as a cornerstone to support multi-metal recovery. What are the advantages of this approach? Increase metal recovery, maximize free metals, and improve selectivity. So how we optimize the blending to achieve that? And what technologies are required to enhance the multi-metal recovery. This example of economies of scope was used by the Japanese smelters. And this is interesting because we have not only the companies, but also the communities thinking in recycling, where a community become an ecosystem of generation of raw materials that can be used in the urban mining processing. So you can find in the internet examples like Dowa, environmental business, or Pan Pacific, or other companies in Japan, or Mitsubishi, who have used this approach for many, many years, not now. This is an example that is in the paper that I showed before and the book that shows a company in Japan, JX, using the interaction between copper, lead, and nickel cobalt to try to improve recovery and maximization of minor and valuable metals. I will not explain the flow sheet, you can see that later, but basically is how a smelter become ecosystem asset to enhance circularity and improve the recovery of more and more metals. This is an example in Kazakhstan, although it's not with secondary materials, it's primary materials where you have copper, lead, and zinc lines doing the same to improve selectivity and increase recovery. So this is what I showed at the beginning. In order to move to a more sustainable mining and metal processing, there are several elements that we need to consider now when it comes to produce the right technical solution. We need to bridge between the miners and the operating plants. We need to put effort in characterization of those materials that are potential to be processed. Search for new application and develop new market. We need open innovation, impact investment, and support incubation of new ideas and business. So, towards eco-processing for an efficient, sustainable recovery of metals, I have been trying to explain that base metals integration will allow a more efficient recovery of minors and valuable metals and safe disposal of metallurgical waste. The valorization of intermediate and waste stream, such as copper slag, will require this multi-metal approach. Impact investment in pre-competitive research is a must. We have to understand and we have to give money for those who are thinking to do that. We cannot wait. We cannot just wait for other industries to come to a solution. It's our problem. We have to invest through that. And I believe impact investment in entrepreneurship are an important step. Integration with industrial waste processing facilities to minimize overall waste generation and maximize recovery of valuable elements. R&D have to be coordinated to be more efficient and agile in providing solutions. One example is how many efforts are done around the world to solve the same problem, and how much coordination we do have among those people who are putting the effort. And I put at the end, and all that should be at the top. Education is a cornerstone to support a metal-based green world. This cannot be left only to the government. Industrial support is also required. A world without metallurgists will not work. In the long term, we understand that there is an evident gap in development between mining countries and consumer countries. The distance between mine, processing plant, and final consumer. How we manage the CO2 footprint of the supply chain. The economic model between miners and smelter has to be reviewed. Penalties on deleterious element as a way of transfer liability might not be the right one for the future. Also, a relevant aspect is the ethical use of copper and the relation to the pricing structure. It is not the same a pound of copper in an electric bus than in a luxury car. But then, how do we price it? Who does collect this premium? How that premium is used? Complexity is here to stay. Complexity challenges in primary and secondary sources will require new approaches for processing of base metals, recovery of critical minerals, and stabilization of those hazardous materials. The multi-metal recovery approach with hybrid processing solution will require new techno-economic solutions based on circular economy principles. Vertical integration with diversification of products, elements and applications shall be considered as enabled to support the growth of an eco-efficient non-ferrous metal processing. We use core chemical properties of base metals. Economies of the scope can provide a platform to support innovative, sustainable solutions by promoting integration and cross-fertilization with other industries. Development of new applications require not only curiosity, but also look across the fence to other industries to jointly develop new products. Finally, eco-processing system integrating new processing of industry waste, and other recycling material, traditional copper ores and other potential sources will be required to a larger extent. Thank you very much.